Hello everyone, welcome to today's session of Faraday Junior's channel, and we'll be dealing with random variables in probability and statistics. So when we talk of a random variable, what is a random variable? In engineering, engineers perform several experiments that involve a lot of uncertainties. When we say a lot of uncertainties, it means the chances of such their outcome being 100% is not assured. So random variables are functions that are used to represent those instances or that give numerical values to those instances. For example, when you ask someone, have you eaten? The person only has two answers to give to you. The person can give you, yes, I've eaten. No, I've not eaten. So in analysis or in probability and statistics, this kind of experiment is what we call qualitative. So in qualitative, it is very difficult for you to be able to perform analysis on such kind of experiments unless you are able to represent this kind of experiment with what? Numerical values. So random variables are simply functions that help us assign numerical values to specifically qualitative events to be able to analyze and get the results we require. So for example, when we consider a sample space S, we can assign a random variable. That is what? X. And X is a member of what? All real numbers. So this is just a notation of how random variables are expressed in what? Probability distributions. So we have two kinds of random variables. And these kinds of random variables are what? Discrete random variables, and we have continuous random variables. So when we say something is discrete, that means that particular distance is finite or it has specific values assigned to it. So if I am giving you a sequence of values 0, 1, 2, 3, 4, and 5, if I've given you these values to work on, you cannot work with values outside these values. So it's either you choose a 0, you choose a 1, you choose a 2, you choose a 3, you choose a 4, or you choose a 5. So I have made your scope finite. You don't have the freedom to do anything that you want. So that is just an explanation of something that is discrete. So discrete random variables have specific values. And they are what? Finite. Or they can have specific sequences. You see, this is a sequence. You can see it's a step size of 1. 0, 1, 2, 3, 4, 5. So the difference is 1. I can also have 0, 2, 4, 6, 8, 10. This is also an example of what? A discrete data. So discrete random variables are what I just explained. So let's now go to some of the probability distributions of what? The discrete random variable, or some of the probability distributions that employ the idea of discrete random variables. So we have the probability mass function, also known as what? The PMF. So as I said, in discrete random variables, you are given a scope. You are not just free to do any kind of thing or to select any value you want. So we are going to look at what? One of the probability functions that utilize the understanding of discrete random variables. And that is what? Probability mass functions. So let's define probability mass functions. So for probability mass function, or for a function to be qualified to be called a probability mass function, one, the probability of all the discrete or the random variable or the values of the random variables declared should be equal to or greater than 1. That means 1. We should have what? Px of what? The random variable being greater than or equal to what? 0 for all values of what? X. That means our probability shouldn't be less than 0. It should be equal to or greater than 0. Then we have the second one, that is what? The sum of all the probabilities taking into consideration the discrete random variable should be equal to 1. That means we will have our sum, you can say from I to n, probability of should be equal to what? 1. So when you sum all the probabilities, it should give you 1. So let's just take an example of instances where you are required to use the probability mass function to make your assumptions. Okay, so here let's consider a coin being tossed twice. So a coin is tossed twice, and you are asked to find the probability mass function when you are selecting a head, or the probability of selecting a head in the outcomes or in the sample space. So you know that we have for a coin tossed twice, we can have head, head, then we can have head, tail, then we can have tail, head, then we can have tail, tail. So you can see that we have what? 4 events. You get it? So if they are asking us the probability of getting a head in all of these, so you can see that here, what will we have? We will have what? 1/4 here. You can see our outcome. We have 1, 2, 3, 4 outcomes, right? So we can have 1/4 here. The probability of getting a head in this event is also 1/4. The probability of getting a head in this event is also 1/4. And the probability of getting a head here is what? 0. Okay. Okay. So let's use this table to solve the example. So here, we want to know the probability of getting a head. So we can call this our x. That is what? Our random variable. So we are using the random variable to assign numerical values to the occurrences of what? This experiment. So we have our x and the probability of our random variable. That is p of x equal to x. So for example, in the first event, we have 2 heads. So we have 2 here. In the second event, we have what? 1 head. In the third event, we have what? 1 head. In the fourth event, we have what? 0 heads. We have 0 heads. So you can see that the probability of getting 2 heads is 1/4. The probability of getting 1 head is 1/4. The probability of getting 1 head and 1 tail is also what? 1/4. And the probability of getting no head at all is also 1/4. So you can see this is the probability mass function for this expression. It simply assigns numerical values to outcomes. So you see, under normal circumstance, there is no head here. So the probability should have given us 0. But in application of random variables, the probability of getting no head is also a probability. You understand? And that is what 1 over 4. So the probability of getting 2 heads here, 1 over 4, 1 head, 1 over 4, 1 head, 1 over 4, and 0 heads is also 1 over 4. So this is our probability distribution. So let's see if it meets our definitions for what a probability mass function is. So we're saying what the probability of x for all values of x should be what? Greater than or equal to 0. So you see 1 over 4 is greater than 0. 1 over 4 is greater than 0. Another 1 over 4 is greater than 0. And this 1 over 4 is greater than 0. That means our first condition for probability mass functions has been satisfied. Let's now go to the next one. And here it tells us the sum of the probabilities of all the events involved in the experiment should give us 1. That means we should have, we can name this our n, n1, n2, n3. Or let's just make it p. So we have our p1, p2, p3, and what? Our p4. So it is telling us that the sum of all our probabilities should give us 1. So here we have to add P1, P2, P3, and P4. If it gives us 1, then this experiment is actually qualified to be classified as a probability mass function. So we have P1 equal to 1 over 4, P2 equal to 1 over 4, P3 equal to 1 over 4, and P4 equal to 1 over 4. So to satisfy this condition, we have to sum all these. And this is what? Simply 1, 2, 3, 4. So 1 over 4 times 4. That will be the sum. And 1 over 4 times 4, you see that it will give us 1. So you see that the second criteria for the definition of a probability mass function has been satisfied. So we see that all the probabilities are greater than or equal to 0, and the sum of the probabilities of each event is giving us 1. So that is what? A probability mass function. And the probability mass function, let's take note, is under what? Discrete random variable. That's where specific values are assigned to x. It is not an interval where you are free to choose any value within the interval, but you are given specific values or a specific sequence to follow.